Hi everyone, and thank you for attending to our fourth talk this year, our fourth webinar. This time featuring Dr. Yang. He's an assistant professor in the Department of Building Services Engineering of the Hong Kong Polytechnic University. He received his PhD from the University of Edinburgh and his bachelor's and master's from the Tongji University in China. Dr. Jiang's research interests are focused in structural fire safety, fire behavior in modern buildings, timber structures, and integrated simulation of buildings and fire. He's been a key developer of the fire version of OpenSys for fire, and now leads a group in PolyU, Hong Kong PolyU, to continuously extend the simulation platform in modeling realistic fire impact and thermal responses to fire. Dr. Jiang, we are honored to have you as a speaker, so the floor is yours.
Okay, yeah, thank you for your introduction, and it's a great honor to have this opportunity. I might just share my screen right now. Okay. Right. So just to double check that you can see the slides clearly, right?
Yeah, that's perfect.
Okay, right. Okay. So yeah, I might start now. Yeah, that's introduced by Julian. I'm Liming Jiang. So I'm currently assistant professor in building service engineering in Hong Kong PolyU. So I'm working in the area of fire safety of building structures. So, and particularly we focus on a lot more on computational modeling, but we also do the testing, experimental test work. So I might start with some kind of challenges in my mind about modeling the building structures regarding the fire safety. So if you check with Wikipedia, there is a definition of engineering. So engineering is the application of knowledge in the form of science, mathematics, and empirical evidence. So it's to the innovation, design, and of structures, machines, materials, software, devices, systems. So see here, if we look at the term structure fire safety engineering, we see these three keywords: structures, fire, which is loading, and we cares about the safety of the structure. And if we are looking at the engineering definition, one of the power tools is a software that we can use, and the software can be implemented with the devices and systems, and to ensure the safety of buildings or structures in a fire. So if you're looking at the two different category of the civil engineering, so one is to design the structures against the earthquake loading. So we have a lot of tools to determine or to estimate the safety performance of the buildings in earthquakes. So we can have a large library of ground motion curves to represent the different levels of the earthquake ground excitation. And we also could do shake table tests and the cyclic loading tests. And also the FEM tools are ready to use for modeling the earthquake engineering or earthquake responses. But for the fire safety engineering side, that currently in most of the countries and the regions, we still adopt the ISO 834 standard fire curve, which is adopts a time temperature curve with uniform temperature distribution. So the design of the structure is based on the prescriptive design approach. So we basically apply fire protection or fire safety measures to meet the requirement for like 2 hours or 3 hours of fire resistance. So this is actually the two different levels of design regarding the different loadings. And so that's why we need to do or conduct a lot of more studies and research to ensure the fire safety of the buildings when the fire becomes kind of major threat to the building. So this is kind of shocking cases, actually. It's totally out of our expectation, especially like in the 911, the WTC tower collapse that what it turns out to be caused by the fire rather than the impact loading of the airplanes. And the recent fire accident from the Grenfell Tower in London, the fire, the scale of the fire, or the scope of the fire hazard is totally out beyond our expectation, and the fire spreading is all through over the whole building. So that posed a question that whether the modern structures are fire safe, and what is the resilience of these buildings in a fire scenario. So thus requires us, or the researchers and the engineers, fire safety engineers, to conduct studies, which may be experimental studies and numerical studies. But what are the real challenges now? So for fire behavior in modern buildings, the left-hand side figure that it was to show the different forms of the tall buildings. So the engineers that design these tall buildings with different frames, mega frames, and also inside the building, the compartment becomes a large open plan of a large open plan space. So that fire occurs in this kind of large open plan compartment. Then the fire behavior is totally different from the traditional sinking, because the standard fire curve that we just mentioned, which is based on the uniform time and temperature curve, is a post-flashover fire scenario. But in reality, when the compartment is large enough, and like in the investigations of the WTC towers, the burning is meant to be localized, and then the localized burning area is actually travel along the floor plan. So that means the uniform time temperature curve, or the ISO 834 curve, will not be valid to use in these scenarios. And for the fire, to determine the fire behavior, it requires a lot more research to characterize this fire behavior. And one of the major movement is to introduce a traveling fire concept. And this Malvia test was conducted by a group led by Professor Jose Turaro, and I think you guys might be quite familiar with. And this paper is written by Juan and other colleagues. So these tests actually demonstrate the different modes of the fire in a large compartment. It starts with a localized, and then it travels. So you see that the fire actually travels from the initial end to the other end, and the flashover occurs, localized flashover occurs at about 270 minutes. So this is not as what we thought about the compartment fire, because normally a compartment fire will have a localized fire as a very initial stage, early stage, and then the spontaneous ignition of all the combustible materials. So they cause the flashover, and then it enters a very high temperature regime. So, but this traveling fire test actually demonstrates that the traditional sinking, or the traditional model for the fire safety design may be not valid in modern structures. And especially for when we're trying to use innovative structure materials like timber, or like CLT, or glulam. So this kind of timber materials also introduce another challenge, because the timber material itself can burn in a fire. So then the fire model will be completely different from like the parametric fire model will be completely different, because then there will be another like surge of the heat flux when the structure members get ignited. So if we kind of briefly summarize that, the different aspects from the loading perspective, that is a fire. So this one is actually a NIST fire test in NIST lab. So the origin of this concern, the safety concern, is the fire impact. So, and the fire will heat the structure members. So that is the heat transfer from the fire flames to the structure section, structure member section. And for the section, for each fiber forming this section, it will undergo material degradation and also summer expansion. So then the structure member, or like here, there's a steel beam, will experience deformation and damage if the fire is large enough. So to understand this kind of behavior from the fire to the structural response after material degradation and summer expansion, two categories of approaches that can be used. So we can use tests, lab tests, or the real scale tests, like here, the NIST test, or the famous Cardington test. That is a whole structure, 8-story building that is a real building scale, and that was tested. And to actually, from this Cardington test, we know a lot of different mechanisms that we have never or paid attention with. So like the effect of the floor slabs. So for the other category, that surely we can use simulation, and because computers now are critical or important in our daily life, that you can use all this computational power every day and in every minute. Then, so the simulation can be conducted with computers, and but what are the limitations? For the test, that the cost and the simulation, we need to adopt assumptions and simplifications, and that's why a lot of researchers so far may be skeptical on the simulation results, because they kind of more confident on the results generated from the test, but they don't trust the results from the simulation because of the lack of the fidelity. But in the end, then we need to use the simulation as our tool, because we cannot do the design using all this real scale tests, right? So that requires a simulation tool to estimate or predict the behavior of a building in a fire. So what is our solution? We adopted, like in the year of 2009. So it's, in Edinburgh, in University of Edinburgh, we adopted OpenSeas as our kind of platform to conduct the structure in fire analysis. So OpenSeas was originated from UC Berkeley, and it was initially designed as an open system for earthquake engineering simulation. And it is open source and is written in C++, and the interpreter scripting language is Tico, and recently then Python was enabled. But for OpenSeas for fire, we kind of reshaped the code, the open source code of the original OpenSeas, and we extend all these modules, and we add new modules to simulate the structure of fire. So we have the fire modules, and also we have the heat transfer, and a lot of the codes for the thermal mechanical analysis. And recently we have Open Fire project that connected to the CFD tool like FDS, and connected FDS to the OpenSeas HT, the heat transfer module. So this actually enables us to do a lot of research, like free our hand that can do or realize a lot of ideas that in our mind when we're doing the investigation, because OpenSeas for Fire is a modular development environment. So you can focus on your own your own code and just the one class, like a material, heat transfer material. So you can focus just on one class, and you don't have to mess up with other codes distributing other projects, because that is just over there. They are ready to use and using the universal standard APIs. And you don't have to write the mesh tools, or you don't have to write the analysis or metrics solver tools. because they are ready to use, and you just use their functions and you can focus on your code. So that actually significantly reduced the learning efforts in conducting the new or computational approaches or the computational methods when you have some ideas of or great ideas of modeling something. That this open source environment significantly reduced the learning efforts compared to the other software package because they are written in Fortran, that is a structure based, so it does not have this modular development environments. So we have a website which is maintained for OpenSeeds for Fire, and you can browse all this information, and also we provide its command manual and examples. So far, this website is still is always under development because we are putting a lot of new codes and new examples along with our published papers. So, but after all, you can follow all of these updates either on ResearchGate, and also you can see the command manuals and examples on this website. So you can search for OpenSeeds for Fire, and you will be guided to this website. So as we mentioned, that for surrounding the OpenSeeds for Fire or within this platform, so we are focusing 3 different aspects of Fire. So we have for the design Fire models, if you recall, we just mentioned that for the earthquake engineering problem, we have a lot of ground motion curves for the earthquake engineering. So we can have the small earthquake, moderate or mediate earthquake, or large earthquakes. So that represent the different levels of loading that can cause the damage or the failure or the collapse of the structure. But for fire, we don't have this library. So one of the vision of this fire library is we can create a lot of different design fire models to represent the different levels of fire scenarios. And some extreme fire scenarios, like we saw in the Grenfell Tower, that is widely spread fire. So that is an extreme scenario, and we need to examine the structure in this scenario, whether the structure could still sustain and does not collapse. And for the moderate fires, we can examine how much of the damage being created in this fire. And that is about the resilience, how long we need to repair after this moderate fire. So that's why we need a library of fire models. And we are adding these fire models in, or making these fire models all variables that in OpenSeeds model. And on the other hand, we have the safety model. So this, we can use FDS to reproduce the fire behavior. And this is another issue about the simulation. And along with the development of the FDS, then the fidelity of the fire simulation will become better and better. And that will be connected, and surely we can connect it to FDS to OpenSeeds HT heat transfer model. We can actually reproduce or this realistic fire behavior and to implement this fire impact to the structure sections. So then we use our built-in heat transfer model to estimate the localized thermal impact or the two-way interaction. That is actually more complicated because the structure failure could cause like the compartmentation boundaries being breached, then will change the fire behavior. So that is our kind of planned move for two-way interaction between the fire and the structure. And in terms of the structures in fire, so we need to look at the global behavior rather than a single structure member, because we know that restraint effects is very important. Because like we just mentioned, like material will have the thermal expansion, like a steel column heated by fire will subject to the thermal expansion, but it will be restrained by the neighboring structures. If you just have a single column test, you cannot capture this restraining effect. And then the failure mode will be completely different. So that's what we learned from the Cartington test. A lot of this column tops are actually seeing localized failure, which is actually due to this restraining effect and this thermal expansion issue. So that's why we need to make our model more larger to cover this global behavior. And when you have these complex sections, like the composite section, steel, tube filled with concrete, this kind of different complex sections, we need to model these sections. And also we need to estimate the effect of the floor slabs. So that will be different from the earthquake engineering models, because that in earthquake, they don't normally need to model the floor slab, because you can use a diaphragm just to make the rigid slab assumption. But in the fire, floor slabs are important, because it will have membrane action, then can have this failure or progressive collapse mechanism, and also the connection behavior. And also when we are saying that we have this new structure material, so that also causes the challenge in the structure modeling. So this is a roadmap of our open seas for fire, and by 2020 and 2020 to 2021, these are almost done. So these different in terms of the different categories or the modules, we have done this work, and we have our planned work that is like after 2021. So then it's gradually editing into the open seas for fire, and we are happy to actually collaborate with other research groups that if you have some kind of findings you want to implement in the open seas for fire or in FEM platform, we can actually help you to implement this. And for the modeling the fire impact, as we just mentioned, we try to introduce or establish a library of design fire models. So it's not limited to the standard fire, parametric fire, and localized fire models. We want to introduce some natural fire models representing moderate and extreme fire scenarios, and also it covers or it represents the traveling behavior horizontally and vertically. So that is our kind of vision for the design fire models to corresponding to the ground motion curves in earthquake engineering. And as we mentioned, that another approach is to connect the open seas with FDS or CFD is fire foam. FDS could be the CFD tools. So that is to create a middleware which transfer the data from the FDS or fire foam to the heat transfer module in open seas. So this is currently ongoing, and we are adding more elements or components into the open fire wrapper. So that is carried out by Atif, which is one of our PhD students in the group. So the open fire is written in Python, and then you will have this drop-down options, and you can choose the different boundary conditions. And there are it's meant to be graphic user interface, and it will simplify the modeling work between the FDS, and so far as FDS and OpenSea's HT. And you can have a realistic CFD model, and you can then implement this CFD model to the OpenSea's HT. So you can either use the AST or AST plus the heat transfer coefficient. We can make some sophisticated heat transfer boundary conditions between the fire and the heat transfer model. So when we're modeling heat transfer, we know that the temperature of the structural member of the section will increase in a fire, and because at the surface that due to the convection and radiation, there will be input heat flux, and also on the unexposed side that there will be heat loss to the ambient air. So when we're trying to model the heat transfer, that some of the questions have been, or problems have been mentioned, that like for the or the localized fire impact, how we address the localized fire impact, and also how to address the heat transfer in some new structural materials like the timber and also other some non-structural material like fire protection materials that should be also modeled in the heat transfer process. And also the damage induced the section change. So that will change the surface or the exposed surface of the structure section. And that the heat transfer will be significant change if the section change, or like the concrete cover being removed, or like due to the spalling. So that will change the depth of the heated region. So this is our the heat transfer issues that we are trying to resolve. So for the localized and non-uniform time variant fire impact, then the heat transfer currently I think it's a reasonable assumption that we model the heat transfer using structure member based. So we analyze the heat transfer in each or single member, like a beam or column or slab. And we have examined that whether we can use a 3D or we can use a number of 2D sections to estimate the heat transfer in the structure members. Because if you use a 3D, then because the heat transfer normally requires a lot more elements to capture the heat gradient, because at the near the exposed surface, the heat gradient, the temperature gradient is significant. So then we need a large number of elements. So if you use a 3D member or 3D heat transfer model, so for the whole building, when the fire is hitting different compartments, then the heat transfer analysis will require a lot of more computational resource. So one of the solutions is to use a 2D sectional analysis. And we found that if the input heat flux is continuous, then we can use this 2D analysis just at the representative sections, then can estimate the heat transfer. So this is for the heat transfer issue and for this concrete and steel structure members. So if we have timber sections, which again showcases the great capability of an open source platform. So we can implement our ideas modeling the timber sections subject to fire, because we know that timber becomes like different layers when it is exposed to fire. And we can have a layer transition be modeled in the timber section, and we can have a tag to represent the different layer and changing from the original wet wood to dry wood and to the char layer. And specifically, we can have the heat generation calculated or modeled in a char layer. So that can address that for the low heat flux environment. Like the heat flux is only 20 kilowatt per meter square, then we know that the timber member can be ignited. But if you're using the Eurocode 5 model, it's a heat consumption model. It does not have any heat generation. So you will never be able to model this kind of situation using the EC5 model. But the only solution is to introduce the heat generation into the char layer. And so that's in our platform, we have added this for the timber sections. And the next step, we are now developing the structure model for the timber components. So this open source and object-oriented platform have enabled us modeling this timber sections and other. We can actually introduce more innovative structure materials if we have the options. If we have a list, we can introduce more, and we can use this software to estimate the thermal response and the structural response, and then we can validate using validate the results using the test. Like here, there's timber sections exposed to fire is validated by this parametric fire curve explorer. So you see that we have a decay stage in this parametric fire, and because the temperature is getting lower, if it is lower than a certain temperature, the self-extinguishment will occur. which is also out of the beyond the capability of the EC5 model. But in here, we can see that our model can capture this temperature or the summer responses quite well. And this is just one of the validation. In our paper, we have presented a lot of different cases using the heat flux and other cases, and like heating and cooling and reheating. So we validated our results. So this again showed, kind of demonstrate how the test or the real test can help the advances of this, the modeling software. So we always need to rely on the tests and the software, but in the end, then the software will be a key solution, because we need to predict the behavior rather than using tests to capture the behavior. So for the structure response to fires, for earthquakes, you may be able to use a 2D plane frame model because also you can, like for earthquakes, you can just use a lumped mass model to capture the behavior because the slab can follow the rigid slab assumption in earthquake. But in fire scenarios that we know in a compartment fire, the slabs and co-working with the beams and columns will behave completely different if we're taking out the slabs. So that's why for a 3D model of high fidelity that we need to model the slabs, which is a great challenge for our work in OpenSeas for fire, because the original OpenSeas does not have any slab model or for a suitable slab model for fire or for earthquakes. So we need to build all these components for the slabs. And after that, I think the next step, we're looking at how to efficiently model a structure, but like this kind of whole structure model or a large model, how to improve the efficiency of this model. So we need to find what are the real aspect or the real factors, and then we need to reduce the scale of the models, or because otherwise we cannot do a faster response or prediction model, especially in the emergency case. We need to very quickly estimate what will be the next failure or the collapse. So for the whole structure model, the traditional one will be the beams. So we use the beams and beam elements or beam column elements to represent the beams and columns, which is quite efficient because it's just like a bar, and you can use uni-axial material to capture the behavior of this flexure beam, and we have this fiber-based sections, and you can have the displacement beam column 2D, 3D, which as a structure model, which it is very common. And for the fire cases, then we have tried to address the localized fire action for these beam elements. So that is another challenge when we have this complex fire behavior, how we model the frames response to the complex fire behavior, like we have fire travels in the floor and vertically. And for modeling the concrete slabs, we know that slabs will have the steel reinforcement. This is only a flat slab. We have the steel reinforcement and as plate rebars, and also the concrete itself is very hard to model, and because the uncertainties and this behavior, because there's cracking behavior of the concrete, and specifically when the temperature of the concrete layer increase, that the material degradation and also the summer expansion issue will further complex the modeling procedure. So this is what we recently published about modeling the concrete slab. This is also in our roadmap from the beam elements, frame beam elements, and then we introduce slabs. And the next step, we'll introduce the composite floor system. So for this floor slab that we see, this is plot, a tensor plot to show the membrane action. So the central region of the slab will actually works like a membrane that can sustain the load in a fire. So that's why we need to model slabs in structure fire scenarios or the cases. And we have, when we are looking at the real steel buildings or structures, we know that composite floor slab with profiled steel decking, and that is kind of a common choice for the steel structures or composite structures. And this kind of geometry shape, which kind of raises the complexity of modeling. So this is in our recently submitted paper. We try to model this composite floor slab in the context of a large model. So we cannot actually use a 3D model, like very detailed model to represent the flat or the thin part and the thick part or the ribbed part. We need to compromise, or we need to kind of achieve a balance between the structure model efficiency and the accuracy. So what we propose is to use a kind of offset reference plane, and then we can have this tapered section to be modeled in the section, in the composite slab section. We kind of package all these definitions in one section, which is a composite floor slab section. So that records what we kind of compliments about the open source, Open Seas for Fire, because we can just focus on one class to realize these modeling challenges or the modeling approach. Here, we demonstrate that we just use a composite slab section, which can deal with the geometry and also the summer action. So you see the geometry that when we have the offset reference plane, that we can have the slabs or the ribs are represented like with a higher thickness, and also we can have this steel decking with layers to represent the material, which are concrete and steel. And in terms of the summer action, we can have an estimation of this the U-shape temperature distribution in this rib section. So this is all packaged in the composite slab section. And we can still use the normal shear elements and all these analysis components. So these are the validation cases. I may not just further explain that, but you can see that what we mentioned about the difficulties, because the geometry, and we need this real fire test to validate our work. So always the test and the simulation should be conducted for to improve our understanding about the different behaviors of the structure in fire. And also we need to model the connections. So recently we are starting to look at the connection behavior. We will have a behavior model for a connection that this zero length element connected to columns to beams, between columns and the beams. And also we can have the element removal technique. So once the connection reaches a limited critical limit of the deflection or deformation, then that means the failure of the connection. So we can remove this connection, and to represent this after the failure of the connection, what will be the structural response and how the global behavior being changed by the removed elements. And we have the other PhD students are working on applying or try to apply all these modeling capabilities for collapse modeling. And like here, this Plastico building, so which collapsed in 2017, and this is a steel building, and the fires again is beyond our expectation. It's not a single compartment fire. It travels vertically and horizontally, and here is this figure actually shows how large is the scope of the fire, and then the structure eventually collapse in this fire. So when we are trying to model this, one tool is to use the GID OpenSys tool. This is also one toolkit that we're developing for the GUI, for the graphic user interface. You can have the further details about this from our papers. And here we use the Revit as a building model, and then we import the GID, the model to the GID to run analysis with OpenSys for fire. So here the modeling the collapse, you can see the effect of the traveling fire and how we capture this deflection. But here, this one is still to show just a grillage model. So the next stage is about we can use hybrid simulation testing. So the idea is that we can have a substructure test in the lab, and we can have the global behavior be modeled with a whole structure model. So that is being conducted with OpenFresco. So which also originated from UC Berkeley and is adopt the same open source framework for experimental setup. So currently we are dedicated to develop the OpenFresco to be a version of OpenFresco for fire. So then it enables that remote synchronization between the global model, structure model, and the laboratory specimen test. So this is the one work that we have presented in our paper in engineering structures. This is a hybrid simulation. So we can have a detailed model representing the laboratory specimen, and we can have which is synchronized through the OpenFresco to a frame structure model, the whole structure model, then which shows the same behavior. But in the end, or the next stage, we need to use the detailed model to capture like the localized buckling and some like the fracture of the fire protection. So these will be another kind of work packages in surrounding or focusing on using OpenSys for fire. So that is going to be a platform for the hybrid simulation testing. So to the end of our presentation, we just mentioned these different opportunities. We can have the short visit from as an incoming visit to PolyU for PhD students. You can have 5,000 per month and in of 6 months in total. If you are interested to visit PolyU, you can have this. You can apply for this, which is funded by our university. And also for the PhD studentship in PolyU, we have the RGC PhD fellowship scheme. It will have very high salary, so it's nearly 27,000 HKD. And also we have the RGC postdoc fellowship. It is funded. It can financially support a period of 36 months, and then annual salary will be 400, more than 400,000 HKD per year. So these are the different opportunities in PolyU, and we are looking forward to kind of visit to UQ, to University of Queensland, and we also welcome you guys to Hong Kong PolyU. So now happy to answer questions if you have any.
Thank you, Dr. Jiang, for your presentation. There are a couple of questions in the chat. I don't know if you want me to read them for you, or you would be
okay. I can check the okay. Okay. So the first question. Okay. So for the Suma. More about the material models in OpenSys other than the EC properties. Is there any work going on? So it is about for the structural materials or the thermal mechanical materials or the heat transfer materials. In OpenSys, we recently, for the steel, we still have this EC-based materials. And for the concrete, for the uniaxial, and we have the multi-axial material. It's primarily this reduction factors will be based on the Eurocode properties or Eurocode model. But you can customize, surely you can customize. And also we try to like introduce this like the least, the node-induced summer string. So there's different properties. And also if you have any specific requests on the materials, then we can help, like we can kind of customize a material model for you. So another question is actually from Qiujing, who's actually my students, that he transfers some kind of model separately. However, they occur at the same time in reality. What do you think of the effect of this difference on structure response and fire? So yes, so the heat transfer, so this is like the loose coupler or closed coupler. So the ideal situation will be kind of integrated analysis, between heat transfer and the structure. But so far, we normally adopted a loose couple, so then which is a sequential analysis. So first we estimate the heat transfer and then the structure. So we need to strengthen this communication between heat transfer model and the structure model, which is the next stage of our work that we need to consider. As I mentioned in the PowerPoint, that we need to address the effect of structure failure to the heat transfer. The second question, whether the OpenCV fire can simulate the local buckling of steel members in fire. Yes, we can. And just mentioning, we can use a detailed model to represent the local buckling of the steel, like the I section we just mentioned. But a beam column element or like a bar kind of element that cannot, which is not able to capture the local buckling. Because the local buckling is the buckling of the flanges and the webs. So it requires, so that's why we need a hybrid simulation model. So we can have the detailed model and also a frame model or the structure or low fidelity model that be connected and synchronized using the hybrid simulation. And also we can have the hybrid testing that specifically we can test the substructure in the lab to capture the local buckling of steel members, or like the fire protection, how the local buckling affects the. Okay, there is a question from Martin. Yes, we are. We have a contact with. There's actually another graduate from University of Edinburgh, Zhao Yu. She is working in McDonald's. And she's very introduced to use OpenCV for fire as a tool for their consultancy work. And we also do this kind of roadshow in mainland China, and we try to kind of present our tool to the industry, and because we need to show what the benefits to the industry, because one of the things is we can customize our software for their needs, and also we can produce or provide a library of fire models which are completely different or from the traditional fire models. We can help them to convince the stakeholders. So that is what we are currently doing. So we are contacting with the consultancy companies, and we try to understand what are the true needs, and then we can commercialize it, or we can help the industry to use it. Okay.
Thank you, Doctor. Thank you for your responses. It seems there is another question.
Yeah, I think there is another question just popping up from Malaysia. Great. OpenCV software application more or less the same as the CFast. No, the CFast is. I think we initially focused more on the structure response to fires, and then we added the heat transfer. And CFast is, I think, is not specific for the structure response to fires, but is more on the fire side, right, and the heat transfer. So we are committed to develop OpenSys Fire as an open source platform, integrating fire and heat transfer and the structural fire responses. So similar work that might be like Sapphire or Vulkan, but we're because different from these, the software is open source, and we are adding a lot of more fire stuff into, or the fire packages into the simulation framework. Okay. There is another question. Motivating grants to develop OpenSys Fire. There are many other software that help you develop for similar goals to be better to improve. Yes, as we mentioned, or I just mentioned, these existing software are not open source, and also these software are written in Fortran, and so this is structure based. So that means all these codes are in a single code file. So it is not easy, or it's kind of impossible for the researchers to customize or conduct further development. But OpenSys for Fire that can enable us to introduce more different modules, and which are easy to implement. And so that's why at OpenSys, the whole community, OpenSys community, is growing really fast, because it offers this opportunity or a platform to conduct further extension. And OpenSys now is not only for the structures subject to earthquakes, but now we have the fire version, and also we have the geotechnical version. So this is the great power of this open source platform. And that's why we recently have added a lot of this fire-related packages into our software platform. If it is in the traditional Fortran-based and not object-oriented, it will be very difficult to add these components. We cannot have this rapid advances of moving forward for adding like sections, materials, or fire and heat transfer modules. Okay. So the great thing is, like, if you, any like research group that if you have, we have recently helped other different research groups that they like them when they implement their studies, like some like for the timber research. We can add these components very quickly based on this open source platform. So we can help them, these different groups to customize OpenSys for Fire and to add the components into the source code package. There is, yes. First of all, I'd like to answer Winnie's question. Is that there has been a lot of efforts in implementing realistic fiber-net scenarios. Are there any data sets that have sufficient environments relevant to structure model used to lecture files? Also, cutting experiments will help. Yes. So this is actually why we need to create a lot of the links and connections between UQ and also other research groups, because we need to investigate the realistic fire behavior, and then we can understand what will be the impact to the structure numbers or the structure itself, right? So the mechanisms of the traveling and rather than flashover is still kind of mysterious, and we see some papers that are publishing and which actually provides a lot of insights on that. But for our kind of currently what we are doing for this part of work, that we need to provide a tool, and along with advances of the fire models, the realistic fire models. So once the fire model, like any kind of new findings being provided, then we can implement this very quickly in this platform. So this is what we want to do. We are not saying this is the end of the fire modeling and a natural fire model, because a library of the fire models is definitely requires a lot of research input. And the open fire platform is, along with the library, we have, because we have the need for the computationally realistic fire. So that's with the FDS or the other safety tool. So open fire is developed for this purpose. So once we have a fire scenario simulated in FDS, how to bridge the FDS model to the HT model in OpenSys and the structure model. So that's why we come up with an open fire platform, which was funded by the GRF project. And Juan saying, any plans for large-scale validation tests? Yes, we are. In this summer we have some small-scale tests in Sichuan, but that is just kind of localized burning test. Yes, if there are some funding for the true large-scale validation tests, which will definitely help for understanding or building up the library of the natural fire models. And yes, and also I look forward to any kind of fire tests that are being conducted in UQ, and that would be great to see the results and help us on the modeling part. Okay. Yes. From it, I understand OpenSys can be used for model behavior instruction. Could it be used to model bowing of aluminum composite panels exploded in flames? Yes, as Julia mentioned, that's one of the great benefits of OpenSys Fire. If we like, we actually, I think somehow but aluminum we don't have included. But that's the point. That's if you're interested in aluminum material, that we can help you develop this code or this material, because if for a single material, it will be quite simple because we have the standard APIs. You can just write these functions very quickly, and according to the research findings, if you know the thermal expansion and the thermal material properties of the aluminum, so then you can implement this in the model. But so far we haven't actually write any codes for the aluminum. We have the stainless steel, but if there is a kind of research need, so that would be great. We can help you implement this. Yeah, thank you, Felix. Yeah, I think this kind of collaboration around the world is because is very important, and we are trying to just provide a platform, and we appreciate a lot of research input that help us. I think the point is the fire safety engineering compared to the earthquake engineering, we are kind of lagging behind. So so we need to kind of yeah, okay. Yeah. All right, great. So, okay. And also, yeah, as I mentioned at the end of this presentation, we have a lot of opportunities that like exchange incoming and outcoming. Yes, yeah, AI. That's why we mentioned this natural fire modeling. So, and also the safety, we need to, because AI is able to generate some variables-based model, and then we can, the AI model can be trained by the real fire state test and the safety models, and then can use this natural fire model kind of as a mathematical description. So yeah, so this is ongoing, and so far we haven't actually moved a significant step for the AI-driven model. Okay.
Thank you very much for your excellent presentation and answering all the questions our attendees had. It's been a pleasure to have you here, and we wish you the best. We will also make sure to forward all the opportunities you advertised by the end of the seminar to all the attendees and all of the members of the chapter.
Okay.
Yeah.
Great. Thank you.
So,
and
thank
yeah,
you very much.
Yeah, keep in touch, and then we can have more joint activities between the Hong Kong student chapter and the
Yep. Of course.
Okay.
Okay. So before ending the seminar, I'd like just to share the contact details for the chapter.
Okay. Yeah.
So to all our attendees, here are our social networks. You can send us an email or follow us on Twitter, LinkedIn. And as you've seen, and most of you registered through Eventbrite, we'll be advertising all of our events in the future. So you are more than welcome to join. Also to look us up on YouTube. We will have a recording of this session and previous sessions, and you will be able to see all of them. Thank you everyone for attending. Thank you, Dr. Jiang, for your presentation, and see you next time. Have a nice weekend, everyone.